Okay, so it's time for us to kick off a new topic, and this is going to be the beginning of our study of calculus. So we'll be doing this over three topics: rates of change and differentiation, where we introduce some basic techniques; applications of differentiation, where we obviously apply those techniques; and then integration, which is the reverse process of differentiation. Here in Year 11 Maths Methods, we only introduce calculus with a very small selection of function types, so really just using polynomial or power functions. In Year 12, we study calculus extensively, and it becomes more complex because we bring in a number of other function types. So we also look at calculus involving exponential functions, log functions, circular functions. So the thing that makes the calculus harder in Year 12 is not that the calculus is different or new, but that you are required to be able to combine your calculus skills and techniques together with your understanding of all the other function types that we've developed throughout the course. So this is where we really want to begin that understanding, which really is so fundamental over the next couple of years and beyond if you were to continue with mathematics studies, calculus being a significant area of mathematics. What we want to look at over the course of the first two videos here is actually not quite yet calculus. The Americans might call it pre-calculus. We don't have such a course, but we want to start to get that sense of the kind of ideas of what calculus is about. So we want to start to talk about the idea of rate of change and gradient, and whether we have constant gradient or non-constant gradient, or whether we're interested in average rate of change or instantaneous rate of change, and all those kind of ideas before we then kind of formalize that into some techniques throughout this topic. So as I said, these first two videos are not particularly mathematical. It's more about sort of exploring these ideas and developing this sense of understanding of what we're looking at. Okay, so let's get started. Today's video we want to have a look at the idea of a rate of change, and obviously the difference between when we have constant rate of change versus non-constant rate of change. So rates of change measure the way that one quantity changes when compared with another quantity. So for example, speed is a really common rate of change that we all are familiar with. It is how distance changes when compared with how time changes. The mathematical phrase we would use there is, how does distance change with respect to time? Okay, that's what speed is, a change in distance with respect to time. Okay. So generally speaking, a rate of change is really just about comparing quantities. It's essentially a ratio or a rate. So if quantity 1 changes with respect to another quantity called quantity 2, Q2, we would be writing the rate of change would be the change in Q1 over the change in Q2. Okay. If we wanted, how does quantity 2 change with respect to quantity 1, it would be, the fraction would be inverted. So the change in quantity 2 over the change in quantity 1. Okay, so let's think about that for a very simple example. The population of a town was 24,000 people in the year 1980 and 56,000 people in 1996. What was the rate of change of the population from 1980 to 1996? Okay, so we want the rate of change of population. And technically it's population with respect to time, but when it's with respect to time, we tend to just call it a rate of change. Okay, if it's a rate of change of area with respect to radius, we would have to say that it's the rate of change of area with respect to radius. But if we just said rate of change of area, the implication would be, how is the area changing compared to time? Okay, so when we sort of omit the with respect to section, generally we're referring to time. So the rate of change of the population, in brackets with respect to time, is going to be, what is the change in the population divided by the change in the time. Okay, so in this case, the change in the population, it was 56,000 minus 24,000 over the change in the time. So from 1980 to 1996 is 16 years. Okay, so what have we got? 56,000 minus 24,000. Hopefully most of you can do that in your head, but just to confirm, so we've got 32,000 over 16, which is going to divide nicely, so that is 2,000. Now let's think a bit about units. Okay, so the rate of change, the change in population, so population is measured in people over the change in time, and in this case time is measured in years. And so therefore our rate of change is in people per years. Okay, so the units of the numerator over the units of the denominator. So the rate of change over the 16-year period is 2,000, is on average 2,000 people per year. Okay, so let's talk about this idea of when we have constant rate of change. So a constant rate of change is one in which the rate of change of one quantity with respect to another quantity does not change. Rate of change does not change. Okay, that's a slightly confusing sentence. So, for example, if we had an empty tank, an empty 500-litre tank, and it's being filled with water at a constant rate, and it takes 20 hours to fill the tank, then the rate of change is a constant rate of change, it tells us that, and it means that we took 20 hours to fill 500 litres, so the rate of change of the volume with respect to time is 500 divided by 20, or 25 litres per hour. And that's a constant rate of change, so that literally means every hour we gain exactly 25 litres. Okay, it's not an average rate of change, although it would also be equal to the average rate of change, but it literally means each time we increase the time by 1 hour, we increase the volume by 25 litres. And we could then proportion that down even further. So, you know, if we then increase the time by 12 minutes, which is 1/5 of an hour, we would increase the volume by 5 litres. Okay, so it's a very, very precise measure, and we know that it is constantly increasing at that rate. And so what that means, if we were to graph the rate of change, if we were to graph this situation, how the volume is changing over time, what we would see is a straight line, okay? Because that rate of change is constant. We know for every 1 hour, we're going up by 25 litres every time. Doesn't matter where you go, 1 hour, 25 litres, okay? So we get that constant gradient if we draw it. So the graph of volume, litres versus time, so we know when time is 0, the volume was 0. When time was 20, the volume was 500. The gradient of this line we know is rise over run, and in this case the rise is 500 over the run, which is 20. And so we've got 500 litres over 20 hours, which is again 25. Now, obviously, a gradient doesn't have units of litres per hour, but the gradient clearly has a connection to the rate of change. In fact, it's exactly the same as the rate of change, and that's one of the first ideas that we want to cement. This idea that gradient is rate of change. Okay. So the relationship between volume and time is represented by a straight line. It has constant gradient, and we've seen that the gradient of the line represents the rate of change. Okay, so gradient and rate of change, they're pretty much interchangeable statements. Gradient is a rate of change. Okay, so I wrote just before that the gradient, okay, we colloquially talk about rise over run. Gradient is, the rise is change in y. Change in y over change in x. That's what gradient is. Okay, so it's the rate of change of y with respect to x. That's exactly what gradient is. Okay, so let's have a look at a second example. Sorry, they've sort of run together there. The graph below shows the distance in meters of a particle from a fixed point O over a period of 20 minutes. Describe the motion of the particle with reference to rates of change. Okay, so making that connection that rate of change is about gradient, that if we have constant gradient, we have a straight line, and therefore we have constant rate of change and all those sorts of things. Okay, so let's have a look at what we've got happening here. So we've got three sort of stages that we want to be able to talk about here. Okay, so we can see that point there, that's got coordinates of 3, 10. We can see that point there has got coordinates of 7, 10. Okay, and then this is 20, 0. Okay, so describe the motion of the particle with reference to rates of change. Okay, now sorry, the units on this axis aren't correct, they're the same as the previous one. So this is time in minutes, it was 20 minutes. Okay, so time in minutes, and it is distance in meters. Distance, from O in meters. Okay. All right, so therefore we know that, let's jot down some points about the journey. So particle starts 5 meters from O. It moves away from O because the distance is getting bigger. Moves away from O at a constant rate of change. Constant speed, which in this case we have a special word for rate of change, which is speed, because it's distance over time. So it moves away from O at a constant speed or rate of change. Okay, and that constant speed or rate of change, we can work that out of, now again, let's think about change in the distance over change in time. So the change in the distance is 5 and the change in the time is 3. At a constant speed or rate of change of 5 on 3 meters per minute. Okay? So it moves away from O at a constant speed or rate of change of 5 on 3 meters per minute. Let's go with until it is, no, let's make a new point, dot point. It moves at this speed for 3 seconds or until it is 10 meters from O. Okay, so then we have the next section of the graph is horizontal. So we can see when it's horizontal, okay, we can think about a couple of things. Obviously that means that during that 4 minute period, sorry, that's not 3 seconds in the previous dot point, that's 3 minutes. Over the next 4 minute period between minute 3 and minute 7, the distance of the particle from O remains at 10 meters. So that means that the particle is staying still. It's staying at 10 meters, okay? There are other things that technically could be happening if we think about the physics of it, but let's not overcomplicate things here. So what we're also seeing during this time period is if we want to refer to rate of change, the rate of change during this time period is 0. The gradient of that line is 0, okay? So it moves at this speed for 3 minutes until it is 10 meters from O. It then remains stationary at 10 meters from O for 4 minutes. During this time, its rate of change is 0. Okay, so then the third phase, so now after a total of 7 minutes, okay, the particle is going to start to move again, and we can see that the distance is now decreasing. So the distance goes from being 10 meters after 7 minutes to being 0 meters after 20 minutes, okay, but it doesn't happen at a constant rate. Okay, so we can see that the gradient here is changing. So initially here it's reasonably steep, gets less steep, less steep, less steep, less steep. Okay, so we've got non-constant rate of change. So basically it starts off quite fast, given that the rate of change in this context is about speed, and then it slows down as it gets back to O. Okay, so what are we saying here? So it then remains stationary 10 meters from O for 4 minutes. During this time, its rate of change is 0. Okay, over the next 13 minutes, the particle moves towards O. Towards O. It does so at a non-constant rate of change. initially faster, so steeper gradient, and then slowing down. Okay, so getting that sense of how gradient changes, what that means in terms of the context, how that connects to rate of change, etc., etc. Okay. Now, I might also add one other thing about that last phase. So while we can't work out the actual rate of change because it's not constant, we do know that the rate of change during those last 13 minutes is negative. Okay, that's because the gradient is negative. The suggestion there is that it's traveling backwards. Over the next 13 minutes, the particle moves towards O. It does so at a non-constant negative. I'm going to note that as well because that's important, rate of change. Initially faster and then slowing down. Okay, so let's think more about non-constant rates of change. So in reality, very few relationships have constant rate of change. For example, it's very rare for a car to travel at a constant speed, particularly in traffic or in a city with traffic lights, and other obstructions likely to cause cars to slow down and speed up. So the graphs of relationships with non-constant rates of change are not linear, and that is that their gradients change. Okay, so they're not going to be, if we were to draw a graph of the rate of change, for most situations we're not going to be drawing straight line graphs. Okay, so below is a picture of an early roller coaster built in Paris, and the path of the roller coaster, height versus horizontal distance, is shown on the graph below. Okay, so we can see here that the horizontal distance travelled by the roller coaster is a total of about 95 metres, and we can see how the height changes over that time. So the rate of change of vertical distance with respect to horizontal distance, that is the gradient of this graph, is clearly not constant. It clearly gets, steeper and less steep, and there is points of zero gradient, etc. So how would we more commonly talk about this rate of change? So let's think about where the rate of change is positive, where it's negative, where it's constant. Okay. So we clearly have negative rate of change where the roller coaster is sloping down. So that would be here, let's say from 0 to 20. Okay. So over the first 20 meters, then here from, I don't know, let's say, maybe 38 to maybe 55. Then it's negative again from here to here, from about 70 to about 85. So just roughly. Sorry, I haven't left us a lot of space here. So it's negative for 0 less than x, which is less than 20. So x is between 0 and 20 meters. And also I'm not too worried about notation here. I've made one particular conscious decision I'll talk to in a second. We're guessing around 38 to about 55, and then about 70 to about 85. Oh, sorry, 70 is less than x, which is less than 85. Okay, and then we want to know where the rate of change. So you'll notice I didn't include 0, include 20, and that's because the rate of change isn't actually negative at 20. The rate of change is actually 0 at 20 where there's a turning point. Okay, so that's why I deliberately wrote less than signs rather than less than or equal to. All right, then where do we have positive rate of change? So obviously where the slope is going up, so between 20 and about 38, between about 55 and about 70, and then between about 85 and 95. Okay, so it's positive when 20 is less than x, which is less than, we called that about 38, when 55 is less than x, which is less than about 70, and again we could have unions between those, but I'm not too stressed about the set notation. I just want us to think about where is there positive gradient, hence positive rate of change, where is there negative gradient, hence negative rate of change. Okay, so from 85 to 90. Where do we have constant rate of change? Now we certainly don't have constant rate of change for any extensive period of time. We technically do have momentary constant rate of change. Well, actually no, because anywhere we could argue that the rate of change is constant just for a moment. So we don't actually have constant rate of change on this graph here. Okay. So there's no sections of the graph where the the graph is straight. Okay, so now we're going to try, and it's going to be a very, very rough sketch here. We're going to try and draw a graph of the rate of change versus the horizontal distance. So let's think about some key points here. So let's maybe, I'm just going to try and sort of vaguely align this here. So let's make that, oh, sorry, let's make that 20 there. Let's go with sort of 38 here. So I'm actually just sort of gradually trying to do that so that they're lined up. Let's make that 38 there. Let's go with 55 sort of here. Let's go with 70 about here. Let's go with 85 about there. And then 95 about there. Okay, so literally just trying to bring those values down from the graph above. So we have a similar scale that we're working to. And again, we're not going to be able to be precise here, but let's think a little bit about shape. So we've just established that between 0 and 20, okay, so when the horizontal distance is between 0 and 20, the rate of change is negative. So our graph is going to be underneath. Okay, we've got negative rate of change. So rate of change has to equal something that is negative, which happens down here. Okay. Now, the other thing we want to think about is how does the rate of change change? Okay, so the gradient is getting less steep as we get towards 20. Okay, so it's clearly got negative gradient, negative rate of change, but it's bigger negative gradient up here, so a bigger negative value, by that I mean, and then it's less, a smaller negative value here. Okay, so essentially, and I'm not going to be able to draw this exactly because I don't really know the shape, but we've got a sense that, let's say at 0, the gradient is something like this, and then it's gradually getting smaller until we get to 20. Now it might not be curving, it might be straight rate of change, but we can't really know. Essentially, it's going to be underneath the x-axis. At 20, the rate of change is 0 because that's where the rate of change changes from being negative to being positive. So it has to go through a moment of 0 at 20. Okay. Then we get positive gradient between 0 and 38. Okay. So my graph's going to be above the x-axis, between 20 and 38. It's going to be back below the x-axis between 38 and 55. It's going to be back above the x-axis between 55 and 70, back below the x-axis between 70 and 85, and back above. Okay, so we're going to need to, again, we don't know exactly what this looks like, but it's maybe going to do something like this, and then it's going to, so the other thing to think about is, so let's think about this, I just drew in that purple section, let's think about the next blue section between 38 and 55. So we've clearly got 0 rate of change here, so then we've got very small negative rate of change here. It's getting a bigger negative value, bigger negative value, bigger negative value, but then about here it starts to curve back. So it gets smaller again as we head back towards here. So that means at about this point, sort of, I don't know, roughly halfway, I don't know that it's halfway, is where we're going to get our biggest negative gradient. Okay, and then it comes back. Alright, so, and then we're going to get similar sort of thing happening in the next bit. Again, I would suggest that with every, let's say, lump of the graph, let me fix it. Again, oh sorry, wrong colour. Alright, so let's say that in here it gets up to, you know, quite high here, then we can see that the gradient on the blue section between 38 and 50 and the purple section between 20 and 38 looks to be about the same. So I should try and make the purple lump and the blue lump around the same heights. But then if I look at the next lump on my original graph, so this section of purple here, it never gets as steep as this one here does. Okay, this is steeper here than what this is here. Okay, so therefore, compared to when I'm drawing my graph, compared to this first purple lump, my second purple lump shouldn't get as high. Okay, and similarly, my second blue lump shouldn't go as low, but it should be this. It should be sort of symmetric with this. Okay, so roughly the same there. So again, we're seeing sort of these two sections, this is positive, this is negative, but otherwise they're sort of the same. Okay, and then the final bit again shouldn't get as high as the previous purple section. Sorry, so not that high. Let's keep it a bit lower. Okay, so we sort of have the rate of change goes from being negative to positive, negative to positive, negative to positive, but it's also gradually getting less steep. So the extremities of the rates of change are getting closer and closer to zero, if you like. Okay, so again, very imprecise, but just really starting to think about that sense of how do I translate between an actual relationship between two variables and thinking about the rate of change between those two variables. Okay, example 3, here we want to look at, again, we want to draw some, very imprecise graphs, but just getting the sense of what's happening. Water is being poured steadily into each of these flasks. For each flask, draw a graph that shows the relationship between the height of the water and the volume that has been poured in. Now, being poured steadily, so the water is being poured at a constant rate. So the volume is changing at a constant rate, but we're not sketching a graph about volume. We're sketching a graph of as the volume changes, how does the height change? Okay. Alright, so as we increase the volume of water in this first flask at a constant rate, the height's also going to increase at a constant rate because we have this nice straight symmetric shape. So let's say, it's simply going to be a straight line. Now again, the gradient of that straight line I don't know without knowing the rate at which I'm increasing the volume, etc. That's not relevant. We're thinking about the shape here. Okay, the second one is part B. So if you think about pouring water in at a constant rate, initially here where the flask is quite wide, for every bit of volume the height won't change very much. Okay, but as the flask gets narrower, each bit of volume will represent a bigger height, a bigger jump in height. Okay, so the volume is going to, as the volume changes, the height is going to change slowly at first, but then it's going to change faster. Okay, so we're going to get some sort of curve that goes in that direction. And then at the very end here, when we're in this top bit, we obviously have a straight cylinder, and so the rate of change at that point will be constant. Okay, so it's hard to sort of, I'm just going to try and make that a bit more extreme so that we can be clear about the difference. So I might draw it as a separate colour. So from this point, it's going to then just start to be sort of just a straight line. So curved initially, and then a straight line. Let me see if I can exacerbate the curve perhaps, so I can make the straight line a bit more obvious. Okay, so the second one here, right, so over the first little stretch here, this bit's essentially going to be the same as what happened in A. For every bit of volume, the height's going to be increasing at a constant rate, okay, but it'll be a reasonably slow constant rate given that the flask is quite wide, okay. Then when the flask narrows, it'll still be a constant rate here, but it's going to be, the height will increase much more quickly here compared to the volume because the flask is so narrow. So, and then we'll go back to that slower increase in height and back to the faster increase in height. So the height will initially increase quite slowly, then it's going to increase quickly, then it's going to increase slowly again, but back at the same rate as this, so same gradient, okay, and then it'll increase quickly again. But again, back at the same rate as this bit because it's the same width of the flask. Okay, so something like that. Again, the precise gradients of those lines can be different. You might have drawn it a bit steeper first and then more steep. Okay, that's fine, but as long as you have the same kind of pattern. Okay, and then finally we have a circular, or I guess it would be a spherical flask. So when you first start to pour water in, the flask isn't very wide at the bottom, so the height's going to increase quite quickly. And then as it gets wider, the height's going to increase more slowly because the water has more space to fill up, and then it's going to increase quickly again. So it's going to increase quickly initially, then more slowly, and then quicker again. So it's going to do something like that, and then at the end you've got the straight line bit with the little neck of the bottle. Okay, finally one more example here. For the graph shown below for x between -3 and 4, inclusive of -3, not inclusive of 4, describe, using interval notation, the set of values of x for which the value of y is increasing as x is increasing. Okay, so this means if y increases as x increases, that's positive gradient. It's the definition of positive gradient. Part B, the rate of change of y with respect to x is negative. So rate of change of y with respect to x is gradient, and we want that to be negative. So this is where do we have negative gradient. and then the rate of change of y with respect to x is 0, okay? So that means 0 gradient. Okay, so we have positive gradient between the two turning points, clearly. So that is when x is between -1 and 2, okay, and it's not inclusive because at -1 the gradient isn't positive. The gradient's going to be 0 at -1. Okay. The rate of change, find where the rate of change of y with respect to x is negative, okay? So we have negative gradient when x is, so remember we know that this is 4 something and we know this is -3 something. So I'm just going to pause for a minute. I'll come back and talk about this. So -3 to -1, definitely not at -1. Union from 2 to 4. Now, talking about these endpoints. Now, 4 is not it's a non-included endpoint. So we definitely can't think about the rate of change of that point. But the other key point is that we also won't include -3 here, okay, in terms of where the gradient is negative. We'll talk in detail about this down the track, but technically at an end point, the gradient is undefined. And that's sort of because we don't know what's happening beyond that endpoint. We'll talk a little bit more formally about that down the track. So I wouldn't worry too much at this stage if you gave a round or a square bracket there, but it should be a round bracket at an end point. We can't calculate the gradient, and hence we can't calculate the rate of change. And then finally, part C, find where the rate of change with respect to x is 0. We've got 2 moments of 0 gradient where the gradient goes from being negative to being positive at the 2 turning points. We call those stationary points. Again, we'll talk more about that. So it's just 2 precise values, so curly bracket set. So x is an element of the set of numbers that contain -1 and 2. All right. Okay, so the work today is from exercise 16A and 16B. Again, this is really just about developing that familiarity and that sense of understanding about gradient, how gradient connects to the original graph, what the graph of the gradient might look like, whether the gradient is changing at a constant or a non-constant rate, etc., etc. So questions there from exercise 16A and 16B.